All chemical reactions involve energy changes, and most often this energy is transferred as heat. So we're going to start to study what is called thermochemistry, which is the study of these heat changes that occur during a reaction. We're going to use the term enthalpy. Enthalpy is the chemistry term for the total amount of heat energy that a reaction system contains. And the enthalpy change, or delta H, will describe whether the system is gaining or losing heat to its surroundings. So let's just really quickly define those terms. The system are the chemicals that are interacting in a chemical reaction, and the surroundings are everything outside of that reaction system. So if I had a solution in a test tube, the chemicals in that solution are the system. The glass test tube is the surroundings, the air surrounding is the surroundings. We could have an open system that would allow more matter to get into the reaction and also heat to transfer in or out. Or we could have a closed system where the actual reaction system is closed off from the surroundings so no matter can get in, but heat is still transferred. And technically we could have an isolated system where the system is so isolated that there's no transfer of neither heat nor matter. Chemical reactions in which heat is released from the reaction system to the surroundings are called exothermic reactions. The chemicals in a hand warmer, that reaction system, releases heat in the process of the chemical reaction that's undergoing. And you, the surroundings, feel that heat as the reaction progresses. Since the reaction system is losing heat, the enthalpy change is negative. Some chemical reactions actually absorb heat from the surrounding to the reaction system. For example, in a first aid kit, we have an ice pack that when you crack the pack and allow the chemical system to mix together, the reaction pulls in heat from the surroundings, and we feel that as coldness. Reactions such as these are endothermic reactions because the reaction system is absorbing heat from the surroundings. And ultimately, because it is gaining heat, the reaction system has an enthalpy change that will be positive. So delta H is positive. But what makes an overall reaction endothermic or exothermic? Well, if we look at these 6 reactions, we see some cases there are bonds being broken, and some cases there's bonds being made. So when bonds are broken, which are all of these scenarios, we see that there's a positive change in energy. Therefore, breaking bonds, if there's going to be a positive change, the system is absorbing energy. Therefore, breaking bonds must be an endothermic process. However, on the other side, whenever bonds are formed, bonds are made, what we're seeing is there's a negative change in energy. Therefore, forming bonds is an exothermic process. So we know it takes an input of energy to break bonds, and then when bonds are made, they release energy. But is this a random amount of energy, or is there a specific value to it? Well, let's look at reaction 3 and reaction 5. In this situation, we're breaking the exact same bond, the nitrogen to hydrogen single bond, however, a different number of this bond. So in reaction 3, we have 4 bonds, and it requires 1,564 kilojoules per mole to break those 4 bonds. And in reaction 5, we have 3 bonds, and it takes 1,173 kilojoules per mole. If we divide each of those values by the number of bonds, what we see is that in both situations, the amount of energy required to break one nitrogen to hydrogen bond is the same value. This clearly suggests that there is a specific value associated with specific bonds. And then if we look at reaction 1 and reaction 6, both of those are breaking and then making the same bond, the oxygen to oxygen double bond. And we see that while one is positive and one is negative, they have the same magnitude, 495. So that means that it takes the same amount of energy to break a bond as the energy released when a bond is formed. So to summarize, every chemical reaction starts with breaking bonds of the reactant molecules, followed by the forming of new molecules in the products. And since energy must be absorbed to break a chemical bond in the reactant molecules, all bond breaking is an endothermic process. You have to put energy in to break the reactant molecules apart. This initial input of energy to start a reaction is called the activation energy. Scientists have experimentally found the average energy needed to break up specific bonds, and they are called bond dissociation energies. And this table below shows us the energy required to break a specific bond, either a single bond in this first table or multiple bonds, such as double bonds and triple bonds in the second table. We know that whenever new bonds are made, energy is released. Therefore, all bond forming is an exothermic process. The enthalpy change of the reaction system is just the difference between the energy absorbed by the reaction system to break the bonds in the reactant molecules and the energy released by the reaction system when forming new chemical bonds. We can calculate this delta H by simply taking the sum of all the bond energies of the reactants minus the sum of all the bond energies of the products. In an exothermic reaction, the energy required to break the bonds of the reactant molecules is greater than the energy released when the new molecules form. This results in a net input of energy into the reaction system and a delta H that is positive. Exothermic reactions are the opposite. The energy required to be absorbed by the reactant molecules to break their bonds is less than the energy that's given off by the product molecules as they form new bonds. Therefore, the delta H of the reaction, the system itself is giving off a net release of energy. Well, let's use this reaction as an example to learn how to put all of this together. We're going to look at the formation of water from its elements. So in this reaction, we have to break the bonds of the elements hydrogen and oxygen, and then form the bonds in the water molecules. So we're going to have to break 2 hydrogen to hydrogen single bonds and 1 oxygen to oxygen double bond, and then we're going to form 4 oxygen to hydrogen single bonds. Each hydrogen to hydrogen single bond has a value of 432 kilojoules per mole, and the oxygen to oxygen double bond has a value of 495 kilojoules per mole. Meanwhile, all 4 of the oxygen to hydrogen single bonds have the same value of 467 kilojoules per mole. When I add up the sum of the bonds that we have to break, that energy comes out to be 1,359 kilojoules of energy must be absorbed to break those reactant molecules apart. And then when I sum up all of the bond energies of the products formed, that will release 1,868 kilojoules of energy in the process of forming those new bonds. So the difference between the input of 1,359 kilojoules and the output of 1,868 kilojoules is that there will be a net release of 509 kilojoules per mole of this reaction occurring. Since there is a net release of energy, this reaction is exothermic because the reaction system is giving off energy to the surroundings. Now let's put this all together with some practice problems. In this reaction, elemental gaseous nitrogen and elemental gaseous hydrogen combine to form the covalent molecule nitrogen trihydride, which is more commonly referred to as ammonia. Write the balanced chemical equation. In this reaction, 1 molecule of nitrogen will combine with 3 molecules of hydrogen to form 2 molecules of NH3 ammonia. Now we have to draw the Lewis structures for each of these molecules to understand which bonds need to be broken and which bonds need to be formed. A nitrogen to nitrogen triple bond is 941 kilojoules per mole, and there's only one of those molecules per reaction. Hydrogen to hydrogen single bond is 432 kilojoules per mole, but from the balanced chemical equation, we see that it is 3 molecules per reaction. So we're going to multiply the energy required to break apart the hydrogen molecule by 3. If I sum these energies together, I find that it takes a total of 2,237 kilojoules per mole to break the bonds of our reactant molecules. Now if we look at our NH3 molecule, it has 3 nitrogen to hydrogen bonds. Each one is 391, but there's 3 per molecule. So that comes out to 1,173 kilojoules of energy needed to break up 1 molecule, but the reaction will produce 2 molecules per reaction. So that means that the sum of all the bond energies of the products will be 2,346 kilojoules per mole. So now to find the delta H of reaction, we just have to take the value for the sum of our reactant molecules and subtract out the value for the sum of our product molecules and see what the difference between those will be. Since the change in enthalpy of the reaction system is negative 109 kilojoules per mole, this reaction is exothermic. Pause the video and try this reaction on your own, and then I'll be back in a second to show you the answer. Okay, well, in this reaction, every 1 molecule of propane will react with 5 molecules of oxygen to produce 3 molecules of CO2 and 4 molecules of H2O. Now, if we zoom in on these structures, we see that a propane molecule has 8 carbon to hydrogen single bonds. Each of those single bonds has a bond energy of 413 kilojoules per mole. And there are 2 carbon to carbon single bonds in there, each with a bond energy of 347 kilojoules per mole. So the amount of energy it takes to break all the bonds in the propane molecule is 3,998. Now, when it comes to oxygen, there's only 1 bond in an oxygen molecule. It's a double bond oxygen to oxygen, and that value is 495 kilojoules per mole. But if we look at the balanced chemical equation, we see that the reaction requires 5 molecules of O2. So we have to take the amount of energy to break 1 molecule apart and multiply it by 5. So it's going to take 2,475 kilojoules per mole to break apart all 5 molecules of oxygen. Then if we look at our product molecules, we have a CO2 molecule that has 2 carbon to oxygen double bonds, each of which have a bond energy of 799 kilojoules per mole. So the full molecule will have a bond energy of 1,598 kilojoules per mole. But again, we have 3 molecules in the balanced chemical equation, so we have to multiply that energy by 3, and that's going to be 4,794 kilojoules per mole of energy released when a carbon dioxide molecule forms. And then the water molecule has 2 oxygen to hydrogen single bonds. Each are going to be 467 kilojoules per mole. That means 1 molecule will be 934 kilojoules per mole. We're going to multiply that by the 4 molecules in the balanced chemical equation, and we're going to see that the total energy released when the water forms is going to be 3,736 kilojoules per mole. We combine these 2 energies for our product molecules, and we see that there's going to be 8,530 kilojoules of energy release per mole of this reaction happening, and there's going to be 6,473 kilojoules of energy absorbed to get the reaction started. And now we have all the information needed to calculate the delta H of our reaction. We're going to take the 6,473 kilojoules of energy required to break the bonds and subtract out the 8,530 kilojoules of energy that is released when the new bonds are formed. And we see that the net change is that there will be a release of 2,057 kilojoules of energy, meaning that this reaction is exothermic.